Students, friends of BSc second sem, I will continue my discussion on transport phenomena in kinetic theory of gases. As I mentioned in earlier classes, that this topic has been divided into three parts. Already I have completed first part up to different velocities of gases, like say average velocity, most probable velocity, root mean square velocity, and the interrelation between them or relation between them. So we will solve some numerical problems based on this at the end. Today I will begin with the second part of this topic, that is transport phenomena in kinetic theory of gases. Hope you remember this. It is mentioned very well in our syllabus, and this topic, as I mentioned, is the most easier one. You can easily understand this topic, as well as you can score the marks on this. Minimum 10 marks question on this, minimum 1 problem on this, minimum 5 marks, and say 1 or 2 marks on questions on this. So we will prepare for this. So to introduce to you the transport phenomena in kinetic theory of gases, a simple introduction. Introduction remains same as the introduction of kinetic theory of gases. Still, as a formality, I will remind that according to kinetic theory of gases, it is assumed that the molecules of the gas are in a random motion. Not only that, molecules of the gas, they behave like a perfectly elastic sphere of negligible but finite in size. Molecules are in a random motion. Due to the random motion, what happens? Molecules, they collide with each other. And we know that the collision is treated here or understood here, it is an elastic collision. Do you know the fact? The scientists, the literature gives us the data. The air molecule, when it is in a random state, that means when it is in a random motion, the molecules of air, they have the collisions, that is around 4 into 10 raised to 9 collisions in 1 second or per second. In 1 second, so many collisions, something into 10 raised to 9 collisions in 1 second. When molecules, they collide, that is when the gas is not in equilibrium condition. Please remember, we are studying a transport phenomena, not at steady state. We are studying a transport phenomena in gases when the gas system or a gas under consideration is in, say, unsteady state or a non-equilibrium condition. We know any system in nature, when it is in unequilibrium, when it is in unsteady state, the system, it tries to attain a equilibrium state or what is known as a steady state. Give an example. Say, in our country today we have a chaos, we have everywhere a pandemic situation, and that's the reason I am doing this a class without students. You are at your home I'm at my home. If I have to say, the people says that stay home, stay free, means stay safe. This is the unsteady state, a random state everywhere. If I touch somebody, I may get infected. That is the fear we have in our minds today, and the policy of the government of India is to make the people not to wander here and there. So what is called as a lockdown, that is to bring the system, the society in general to a steady state, to a normalcy. We want to live our life a normal life. But today, this month, that is say May, June, April or a March, part of March, is not a normal period for us throughout the country. We are having the second wave of this, what is called as pandemic. Now this is unsteady state, a state which is not a normal. So this is a situation can be applied to gases. When the gas is not in a steady state, we have to bring our gas itself, we need not try to do it. Gas itself comes to a normal state, tries to attain a equilibrium state. When it is in a random state, the molecules, they move with different velocities in a different direction. They collide. When the two molecules collide, the direction and the speed changes. We know that. So here, when the molecules are in a random condition or in unsteady state or not in equilibrium condition, certain things, the physical quantities, the physical parameters of the system of gases, they tries to bring it to the steady state. During its random state, during its non-equilibrium condition, parameters like momentum, parameter like heat energy, parameter like mass, they get transported from one point to another point when the system of the gas is in unsteady state. So we are discussing a phenomena when the system of the gas is not in a steady state, what happens during that? And that state, say the certain parameters brings that unsteady state or inequilibrium condition to equilibrium condition. It's not that easy, equilibrium to this one. Government, the entire system of the government and all is after that to bring a normal life in our country, or even the entire world is trying to bring the normalcy or a normal life of a human being. So many things are in place. Well, so here a transport phenomena in unsteady state or in non-equilibrium condition, the molecules, they have the momentum, because the molecules are in random motion, they have the different velocity. We say velocity is equal to, say momentum is equal to P is equal to mass into velocity. Every molecule has mass and it moving with a different velocity. So we have what is called as momentum. So momentum of the gas molecule gets transported from one layer or one region to the another region. That is one point to be remembered. When gas molecule is in a random state, what is called as thermal, there will be a thermal agitation. There will be thermal agitation. During that, the one layer or one region of the gas molecule are having more energy. The molecules in its unsteady state or non-equilibrium condition will have more energy, and the system always tries to bring or comes to the steady state, that is gas molecule. Gas molecule or gases tries to attain or tends to attain equilibrium condition. During that process, energy, that is heat energy, gets transported from higher energy or higher temperature to the lower temperature, and that leads to the transport of energy, transport of momentum, transport of momentum, transport of momentum leads to the, or it makes us to study viscosity. Already you have studied this, probably I have taught you. This is one. The second, the transport of heat energy or energy, that is transport of, you can use the word transfer of heat energy or transport of heat energy, or you can say a kinetic energy, leads to thermal conductivity or conduction, thermal conductivity. And bodily, in a gas, when a gas is not in equilibrium condition, there will be unevenness of a mass, there will be uneven concentration of gas molecules. So molecules are moving from a higher concentration region to the lower concentration region. There is a transfer of mass. So the transportation of heat energy leads to the thermal conductivity. Transportation of mass or transfer of mass leads to the transfer of mass or transportation of mass leads to the diffusion. So here viscosity, thermal conductivity and diffusion is the result of transport phenomena in kinetic theory of gases. So we have to derive the expression for this, and the expression for diffusion coefficient, expression for coefficient of thermal conductivity, expression for the coefficient of viscosity, and the expression for the coefficient of diffusion. These are the important or the key derivation in our syllabus, bound to be 10 marks candidate for examination. So meanwhile, this is, say I wanted to say something about introduction to kinetic theory of gases, that to transport phenomena. Let us come to the another point. We say when gases are always, or gas molecules are always in a random motion. When they move with a different velocity ranging from 0 to infinity, and when the molecules collide with each other, their direction, their speed changes. When the molecules they collide with each other, I have given an example. When air molecules collide with each other, number of collisions taken per second are in the range 4 into 10 raised to 9 collisions per second. This is one example. When a molecule collides with each other, after collision it changes its direction and say speed. Between two collision, molecule travel or propagate certain straight line path. and the straight line path between any two collision is called as its free path, right? If I'm moving in a market, right, and there are many, so if I'm moving without anybody here, I will move up to that person, and then I meet with another person, I will change my direction. So this is, so these are the molecules, dots are the molecules. I will represent here in a picture. You will come to know, you will have an idea about this. These are some molecules randomly distributed. So I will draw some path here. Okay, so they move in a different direction, right? Say this way, say this way. This is, say this is, okay, this, and then this, okay, this, say here, again it goes here. So this is a zigzag path. So this is one molecule position, this is another molecule, they collide. After collision they travel this path, and this path is known as free path. The distance between two molecule or two collision here, free path, and the path is a straight line path. And if you take the average of this path, the average path between the successive collisions of the gas molecule is known as mean free path. The average distance, say here. So the term mean free path is used, and it is defined as the average distance traveled by the gas molecule between two successive collisions is known as mean free path. It is the distance, say average distance, this distance plus this plus this plus all the distances, straight paths are counted and then divided by a number of collision, that gives the average path. I have given an example here. In air molecules, they have the number of collision in 1 second are this, and the average mean free path for molecules is about, say, it is denoted by Greek letter lambda. It is 10 raised to -7 meter. Such a small distance it is, but the distance is a straight line path, and it is called as mean free path. Let's go for the expression for mean free path. Well, there are two expressions given by the two scientists. This expression is known as expression for the mean free path, and this expression you can say lambda is equal to simply total distance traveled divided by the total number of collisions, S by N. It's a common say here. It is common. Now this you can write down the average time. This is average mean free path. Average distance between successive collision is called as mean free path. The average distance, say time between two successive collision is, say it is equal to lambda by C, the average distance. C, the average distance or the average velocity. This is our mean free path. This is mean or average velocity, and this is called as average time. Average time, mean free time. You can call this as tau, the mean free time. It's not mentioned in our syllabus, mean free time. That is the average time taken by the molecules between two successive collision. It is given by the ratio, that is mean free path divided by the average velocity. Let us go for the expression first derived by the Clausius. Clausius expression, I am not going to derive the derivation because it is not mentioned, the derivation is not there, only qualitative discussion on mean free path. Clausius expression for mean free path. That is lambda. As the first person to find this. For this, let C be the average velocity of the gas molecule at steady state. Let's say sigma be the diameter of a molecule. Here we have assumed that every molecule is spherical in size, identical sphere. When one molecule collides with another molecule, say here they have what is called as sphere of influence, and the diameter of the sphere of influence is equal to 2 times sigma, where sigma is the diameter of a molecule. So if sigma is the diameter of the molecule, assuming molecule is a spherical in shape, the expression, this Clausius arrived at an expression for mean free path, and this expression is given by this 1 upon pi sigma square n, where n are the number of molecules per unit volume, number of molecules per unit volume. Sigma is the diameter, half of that is the radius, pi is a symbol, and this is known as expression given by Clausius. Let us look at this expression. I am not deriving this. Look at the expression. On what basis he has arrived at this expression? He made two assumptions. One, see, he assumed, which is basically wrong one, all the molecules are at rest and the molecule under consideration, the only molecule under consideration is in motion. So that is one assumption. And the assumption made by the Clausius is basically wrong. How come all the molecules are at rest? You cannot find in a gas molecule or in a gas system molecules are at rest. Basically, it's a wrong assumption. Still, we are having this in our syllabus. The reason is he is the beginner. He has started finding the expression for mean free path, and though for each simplification to arrive at the expression, he had made the assumption, though it is wrong. The second assumption made by him, the sphere of influence. If I draw this properly, this is one sphere, this is another sphere, here is one more sphere, and if they collide, you can draw one more sphere, and this sphere here is called as sphere of influence. The diameter of the sphere of influence is 2 times the diameter of individual molecule. Assuming gas molecule is a spherical in size. So based on these two assumptions, he has arrived at this. This is not accurate, expression, it is approximate expression. Later on, Maxwell corrected this, and that expression is known as Maxwell's expression. In Maxwell's expression for mean free path, Maxwell's expression for mean free path, what he has said. Maxwell obtained an expression, derived an expression for mean free path based on the assumption all the molecules are in motion. He corrected Clausius' assumption all the molecules are in motion and the molecules are having steady, say, velocity, constant velocity, and he applied his famous law of distribution of velocity called as Maxwell's law of distribution of velocity. And using Maxwell's velocity distribution law, the Maxwell obtained the expression for mean free path, and that is this: lambda is equal to 1 over root 2 pi sigma square into n. All these things are correct. Only thing, we have added this factor, and by adding this factor, this is known as Maxwell's accurate or most accurate expression for mean free path. Please remember, for all the solving the numerical problems or for all the other discussions, we are going to use this expression called as Maxwell's expression for mean free path, and this is found to be a corrected expression. Correction suggested to the Clausius, only 1 over root 2 is not here, which is here, and many times in physics we have come across such things. For example, velocity of sound in gaseous medium. That is, somebody has suggested one formula and later on Laplace has corrected, and then we call it as, that is Newton's Laplace formula for the velocity of sound in air medium. Newton has first suggested, later on it didn't give a proper value of the velocity of sound in gaseous, and later on Laplace has corrected. Sometimes we call it as Laplace correction or Newton Laplace formula for the velocity of sound. Similarly, we have the other concept even in physics other than this. So this is the expression for Maxwell's expression for mean free path. Let us go for how does this expression, that is for mean free path, varies with temperature and pressure. Variation of lambda, the mean free path, variation of lambda, the mean free path on, or variation of lambda with, we can write with temperature and pressure, with temperature and pressure. Fine. Let us see, this is important for us. For this, let us consider 1 mole of an ideal gas, amount of ideal gas, and we have this PV is equal to RT, the ideal gas equation. Let me divide this gas by N, that is Avogadro number, N the Avogadro number, P the bar pressure, B the volume, R is the gas constant, T is the absolute temperature, PV by N, say RT by N, by dividing on both sides. So let me solve for P. P is equal to, the pressure is equal to, say N by V into RT by N. So this n gets cancelled. This pressure P is also given by an equation. P is equal to N K T. N are the number of molecules per unit volume. Capital N is the Avogadro number. K is the Boltzmann constant. T is the absolute temperature. Let us take this per unit where N is the number of molecules per unit volume, and this N is equal to capital N per unit volume V. We know this K, the Boltzmann constant, is equal to R by N. We have used this in earlier discussion. So let me write N is equal to P. N is equal to P by KT. P by KT. Let us substitute this N, the number of molecules per unit volume, in terms of pressure, that is Boltzmann constant, and absolute temperature. We have the expression for mean free path. Let me write lambda is equal to 1 over root 2 pi sigma square into N. N is the, all other things are constant here, only the N varies. Let us substitute that. Lambda becomes equal to 1 divided by root 2 pi sigma square. N is equal to P by KT. So here it becomes KT by P. Now we have this expression for mean free path. Look at the expression. Lambda is equal to 1 over root 2 pi sigma square KT upon P. Root 2 is constant, pi is constant, and for a given gas size is constant, the diameter is constant. Look at this. Lambda, the mean free path, K, the Boltzmann constant. It is dependent on these two. Mean free path of the gas is directly proportional to the absolute temperature. Please remember this. Mean free path of gas is directly proportional to the absolute temperature, and also mean free path is inversely proportional to the pressure. Inversely proportional to the pressure. And this is how, as the temperature of the gas increases, mean free path of a gas increases. I have given, that is 10 raised to minus 7 meter, the lambda for air molecule at room temperature. At room temperature, if the temperature increases,